Good morning, sir. So, welcome to this second day parallel session, Hall B here. So, for this session, will be coordinated by Dr. N. Rajagopal. He is one of the prominent NWP scientists in India. He was the director of NCMWF India for a long time and one of the best scientists in NWP and also Ministry of Arts and Awardee. And in addition, he is the also main person behind the development of whole high power computing system within the Ministry of Arts and Science. So he is one of the best person to for monsoon modeling, and also he one of the prominent scientists in monsoon mission. So welcome to this session, sir. Now it is up to you, sir, to coordinate this session.
Am I audible? Good morning to you all.
Yes, sir. Yes, sir. You are audible, sir.
So this session has got, I think, 6 papers, and we have to finish in, I think, by 10:30, 11:30 rather. So each paper has 10 minutes of presentation, 2 minutes for discussion, 1 minute is just for changing over, I think. So the first paper, Arati Menon, modeling a monsoon process team, the role of tropospheric and tropospheric moistening and land surface wetting in the progression of 2016 Indian monsoon.
Sir, before you start, sir, one announcement, sir. Before you start,
yes.
Sir, people will be asking questions from this direct session or as well as from YouTube. So YouTube questions will be forwarded to you in the chat box, sir. And all the admin IMD will be providing that question to you, sir. Then you can allow the questions for the session, sir. Okay, thank you, sir.
They will be able to see the questions also, others?
That will be pasted on the chat box.
Okay. Okay. Aarti, you can start. You have 10 minutes.
Sir, let me share the presentation.
Can we have it on full screen? Yeah, fine. Go
yeah.
ahead.
Okay, yeah. Thank you, Dr. Rajagopal. Good morning, all. I will be talking about the role of tropospheric moistening and land surface wetting in the progression of the 2016 Indian monsoon. It's 4:30 in the morning here. Apologies if I'm a bit sleepy. Just to give a quick background, as you all know, India receives more than 80% of the annual rains during the monsoon season. I'm just trying to minimize this so that I can see the figures. However, modeling and forecasting of the monsoon is limited by inadequate representation of subgrid scale processes and a lack of adequate observations to understand these processes in detail. For example, if you look at this figure, this shows the rainfall biases from the CMIP-5 multimodal mean. We can see that a strong dry bias exists over India and a wet bias over the equatorial Indian Ocean. And the bottom figures shows the rainfall biases in the CMIP-6 multimodal mean compared to the CMIP-5 multimodal mean. And we can see that the dry bias still exists over in the CMIP-6 set of models. However, the biases are slightly reduced in the CMIP-6 models compared to CMIP-5. The Encompass project was a joint initiative between the UK and the Indian Ministry of Earth Science, and the project aimed to improve the Indian monsoon forecasting capabilities by gathering more observations and by doing high resolution modeling. And as a part of the project, we did a field campaign in India in 2016, and we also did some high resolution model simulations of the monsoon. And in this talk, I will be showing results from the high resolution modeling of the monsoon. The slide is not moving forward. Yeah. The figure here, this animation shows the progression of the Indian monsoon onset isochrones. We know that the monsoon onset takes place in the southwest of India and the northeast by around 1st June, and it propagates in a northwestward direction. So the monsoon propagates in a direction perpendicular to the direction of the mean flow. And in this talk, we will be looking at some mechanisms which affect the northwestward progression of the monsoon. Now, coming to the model setup, for the study, we have used the nested suite setup of the MET-OFIS unified model. This figure here shows the limited area model domain, this outer box. The limited area model was ran at different resolutions like 4 kilometer and 17 kilometer resolution. The 4 kilometer meter model was convection permitting, and the 17 kilometer model had parameterized convection. The simulations were run for a period of 153 days from May to September 2016. We are specifically interested in this year because we had the field campaign during this period. The 4 kilometer models were ran using two different land ancillaries, the International Geosphere Biosphere Program Land Ancillary and the Climate Change Initiative Land Ancillary. So this was done to understand the effect of the land surface boundary forcing in these processes. The limited area model was driven at the boundaries using the global model. Now, let's see how the progression of the monsoon was in 2016. Here, each panel shows the pentad mean rainfall from the beginning of June to mid-July. We can see that during the beginning of the season, the rainfall is mostly concentrated over the southern parts of India. And as the season progresses, the monsoon rains propagates in a northwestward direction, and then by around mid-July, the entire country was covered with monsoon rains. So now we will look at two different mechanisms which could have affected the northwestward progression of the monsoon. And one mechanism is the effect of dry air intrusions, which was put forward by Parker et al. In 2016. So what is shown here are the spatial pattern of relative humidity and winds from ERA interim reanalysis and the three models, that is the 17 kilometer model and two 4 kilometer models that use different land ancillaries. So here we are showing relative humidities and winds at 600 hectopascal as well as 850 hectopascal. So if you look at this figure, that is during the end of May, we can see that there are strong northwesterlies in this region which carry dry air from all the way from the Afghanistan region towards Head Bay of Bengal. So these strong northwesterlies at around 600 hectopascal are the northwesterly dry air intrusion. So we can see that as the season progresses, as the monsoon onset takes place, this moist monsoon flow is taking over, and the mid-tropospheric dry air intrusion is being eroded from the southeast. And by around July, these northwesterlies changes their direction and become northerlies and start flowing towards the Arabian Sea. So all these models captured the this mid-tropospheric dry air intrusion of 2016. Now, to look into more detailed thermodynamics of this dry air intrusion, what is shown here is the time pressure section of different thermodynamic parameters at a location called Nagpur, which falls in the path of the monsoon progression. So in this panel, the shadings shows relative humidity, and this black dashed line shows the freezing level. In the x-axis, 0 represents the time of local onset at Nagpur, the day of local onset at Nagpur. So towards the left, we have 30 days prior to onset, and towards the right, we have 30 days after onset. And we can see that about 20 days prior to onset, the relative humidity increases in the mid-troposphere near the freezing level, and this high relative humidity layer starts deepening. And as the onset approaches, we can see that after that, the entire atmospheric column is highly humid with relative humidity above 60 hectopascal. The bottom panel shows theta E, equivalent potential temperature. So we can see these low values of theta E near the freezing level, and this shows the mid-tropospheric dry air intrusion. So 30 days prior to onset, we can see that there is a deep layer of this dry air. But as the pre-monsoon rains occurs, and as the mid-troposphere starts moistening, we can see that this is eroding this dry air intrusion, and the dry air intrusion is almost absent once the onset takes place. So what happens here is that as the congested clouds and cumulus clouds associated with pre-monsoon showers, when they start to penetrate the freezing level. Okay, yeah.
2
When they,
minutes.
yeah, thank you. When they try to penetrate the freezing level, they result in detrainment and moistens the mid-troposphere, which will slowly erode the dry air intrusion. Now, looking at the second mechanism, that is the effect of land-atmosphere interactions in the progression of the monsoon. Here, the two blue lines shown here are the area averaged rainfall over the core zone from the two 4-kilometer models which use two different land ancillaries. And we can see that this rainfalls is there is not much difference in the rainfall between these two simulations. However, if we look at the sensible heat flux H. So here the red line shows the mean sensible heat flux averaged over the core zone at 6:30 UTC. We can see that during the beginning of the monsoon season, that is during May, when the soil is relatively dry, the sensible heat flux is large, and the precipitation is affected by the small changes in soil moisture. And because the sensible heat flux is dominating the evaporative fraction and results in the changes in rainfall. But during June, as the monsoon approaches, we can see that the sensible heat flux decreases. And in July, when the soil is totally moist, there is low values of sensible heat flux, and then any small changes in the soil moisture do not have much effect on the evaporative fraction or the changes in the rainfall. The blue lines here shows the spatial variability in sensible heat flux over this region. And we can see that they are entirely different between, like there is a strong difference between the CCI and the IGBP simulations. So when the spatial gradient in sensible heat flux is stronger, that results in localized mesoscale circulations that can trigger localized rainfall. This was shown by Barton et al. For northern India.
Can you conclude? Time is up.
Yeah. So to conclude, the 4-kilometer simulations capture the mid-level dry air intrusion. And the main point, what I want to say here is that during the beginning of the onset, the land surface plays a major role in the progression of the monsoon by affecting localized circulations and increasing boundary layer moisture. But once the soil
It's
is...
enough. You don't have to
Okay.
read, then people will read.
Okay.
Thank you. Thank you, Arati.
Thank you. Yeah.
Are there any questions? So there are no questions on the YouTube. I don't see anything.
Okay.
So why did you choose 2016? Just because encompass data, is it?
Yeah. So we were doing some case studies and all for that year, basically, so that we can compare with the flight observations and radar observations and all.
Okay. Any other questions? I don't know. Anand, anybody is there? Okay. And thank you, Aarti.
Thank
for
you.
the presentation.
Thank you.
Thank you. Yeah, the next paper is by Akash Sharma.
Good morning, everyone.
Can you come on the video? Can you put on the video so that we can see you for once at least?
Good morning,
It is
sir.
Indian summer monsoon. Good morning. Indian summer monsoon intercomparison of Cordex core and Cordex essay. So
Yes,
you're
sir.
from
So shall I share my
you're
screen?
from IITM? Yeah. You're from where?
Sir, I'm from JNU. I just
Okay.
started my PhD thesis under epidemiology, sir.
Okay, I understand. Okay, go ahead. Once the screen comes on, I'll start your clock.
Sir, is my screen visible?
Yeah, okay.
Yeah, it's visible.
Good morning, everyone. I am Akanksha Sharma. Today I'll be presenting on the topic Indian summer monsoon intercomparison in Codex core and Codex essay. We all know Indian subcontinent gets higher amount of precipitation during June, July, August, September due to Indian summer monsoon. Indian summer monsoon is a regional phenomena, so GCMs are not able to capture its dynamic and physical processes due to their coarser resolution. So dynamical downscaling is done. Codex is one of the initiative by WCRP in which in the first phase of Codex downscale RCMs are utilized to downscale the GCM at a finer resolution of 50 kilometers, and in the second phase the downscaling is done to achieve a finer resolution of 25 kilometers. In the present work I'll be intercomparing Codex SA and Codex Core by studying spatial temporal distribution, intraseasonal interannual variability and intraseasonal oscillation. The flow of my presentation is as such. First of all, I will be discussing precipitation climatology of both the model, then precipitation bias, intra-annual variability, probability distribution, temporal distribution, intra-seasonal oscillation, and then conclusion. This figure shows JJS mean precipitation of Codex core model experiment with corresponding IMD observation. The precipitation maxima over The precipitation maxima over Western Ghat, Northeast India, and Central India are well represented by all the experiment models. Now, if we look at the model experiments, you can see higher precipitation is observed on the leeward side of Western Ghat. This is maybe due to forced moisture transport on the leeward side and uplifting of the moisture. In Remo model experiment, reduced precipitation is observed along the foothill of Himalaya, whereas higher precipitation is observed below the monsoon core zone or central India. In Cosmo model experiment, almost all of the Cosmo models shows precipitation or resemble precipitation to IMD. This is also reported by Maharana et al. 21. Whereas in Codex SA, RCA model experiment underestimate precipitation over northeast India, whereas overestimate precipitation on the central India. In Regacia model experiment, all the precipitation maxima over Western Ghat, northeast India, central India are underestimated. There are few models which are common in Codex SA and Codex Core, like when RCM is downscaled from MPI ESM and ERINT, it shows better precipitation for in northeast India, central India in Codex SA initiative, whereas in Codex Core it shows better precipitation over northeast and Central India. In Codex SA, it do not show precipitation in a better manner, whereas it overestimate precipitation in the northern India. When REMO is forced from MPI ESM LR in Codex score, it do not show much improvement. This figure or this slide shows precipitation bias of Codex score model experiment. From this figure, we can say that Cosmo model experiment shows moderate bias or moderate dry bias across major part of the India, whereas a Regia model experiment shows wet bias over southern India due to local monsoonal scale circulation and associated moisture transport, whereas Remo model experiment shows wet bias over central India except for the downscaling carried from NOR-ESM. In Codex SA, RCA model experiments shows wet bias in the central East India, whereas Regia model shows wet bias over North India. The common model from Codex SA and Codex Core shows wet bias, like for this MPI ESM MR shows wet bias in the North India, whereas in Codex Core it shows wet bias over the South India. The Northeast India in the Codex Core shows wet bias, whereas in Codex SA, dry bias is observed in the Northeast India. From this, we can see the spatial distribution is well represented by Codex Core in comparison with Codex SA. This figure shows daily precipitation averaged over Indian landmass from 1979 to 2005. If we look at the IMD observation, we can see from 1979 to 1985, higher precipitation is observed in the month of July and August. Whereas as we move towards 2005 onwards, a higher precipitation is observed in the month of August and September. From this figure, we can say precipitation is shifting from July-August to August-September. Along with the shifting of precipitation, higher intensity of precipitation is observed in recent year. If we look at the Codex Core model experiment, only two models when REMO is downscaled from head gem and nor ESM, only these two shows the shift in precipitation, whereas intensity of precipitation is not captured by any of the Codex Core model. In Codex SA, none of the model capture either the shift of the precipitation or the intensity of the precipitation. From this, we can say the spatial distribution is represented by Codex Core better, but this daily precipitation is not represented by any of the model. This figure shows probability distribution of precipitation intensity from June to September during 1979 to 2005. A is for Codex Core and B is for Codex SA. If we look at the Codex Core, we can say that curve of all the black line here shows this black line is for IMD observation. Almost all the models shows similar mean but skewed. The variability is seen in Codex Core in comparison with Codex SA, as it can be observed from the spread of the distribution. More moderate to higher precipitation is observed in Codex Core in comparison with Codex SA. So we can say that both the model shows certain amount of uncertainty. To see this uncertainty, this temporal distribution is plotted. This plot shows the temporal distribution of mean monsoonal precipitation averaged over Indian landmass from 1979 to 2005. These bars represent the plus minus standard deviation of gray bar is for IMD, orange bar is for Codex Core, green bar is for Codex SA. Black
you have
line.
2 minutes more. 2 minutes more.
Okay, the black line within the bars represent mean of each ensemble of the Codex Core, Codex SA and IMD. Here, whiskers represent maximum and minimum value. we can see for few years mean of Codex score is closer to IMD, but Codex SA shows more variability, whereas standard deviation plus minus 1, maximum and minimum value of both the models shows great variability. From this we can say both the models show certain amount of variability or uncertainty. This may be because of internal variability of the GCMs and RCMs, or the physical and dynamical processes of both GCMs and RCMs. And at the last, we plotted intra-seasonal oscillation. We tried to see intra-seasonal oscillation. For this, lag composite of July-August precipitation during active and break spell is observed in IMD, Codex score, then Codex SA. Active spells are computed on the basis of standardized anomaly with standard deviation value greater than or equal to plus 1 standard deviation for 3 consecutive days is defined as active days, whereas standard deviation less than or equal to minus 1 for 3 consecutive days is defined as break spells. Here you can see the northward propagation of precipitation is better observed in Codex score model. In Codex score experiment, whereas from lag 4 to lag 8, Codex SA better represented, or it resembles more to the IMD observation. This similar pattern is observed in break phase or break spells. From lag -8 to lag 2, Codex score resemble it more, whereas from lag 4 to lag 8, Codex SA better resemble the precipitation or better resemble the precipitation from IMD observation.
Please conclude.
And at the end, in the conclusion, I can say Codex score suit represents spatial distribution and temporal distribution better than Codex SA. Out of Codex score, Cosmo model experiment resemble more towards the observation. Among all the models experiment which are similar in Codex score and Codex SA, and downscaling from MPI ESM LR over RAMO is more do not show any improvement. The shift which the precipitation shift in the monsoon or a precipitation shift in the IMD observation is not captured by any of the model experiments. So a great amount of uncertainty is seen.
Fine.
Thank you.
Thank you. There are two, I think, few questions in the chat box. Can you answer them?
Yes, sir.
There are two questions in the chat box. Can you answer them?
Codex simulation are for what period and are forced with what boundary condition? Codex score, Codex is used for 1979 to 2005, and the boundary condition of various GCMs are used. In Codex score, there are around 12 GCMs which are used to downscale. And what is the difference between Codex score and Codex SA? Codex score has a resolution of 25 km, whereas Codex SA has a resolution of 50 km. So intercomparison is seen on the basis of this resolution. We studied spatial, temporal, annual variability, and intra-seasonal oscillation to compare or to see the improvement in Codex score.
Okay. Thank you very much.
Thank you, sir.
Akka.
Thank you.
Yeah, our next speaker is Niranjan. Niranjan? Yeah, he will speak on atmospheric kinetic energy spectra from global and regional NCMRW unified models. So can we start? Niranjan, can I see you for some time?
Yes, sir. Yes, sir. Sir, am I audible?
You can start.
Yeah,
we are audible. Go ahead, we're starting.
Okay, sir. In my screen is full screen, no?
Yeah. Go
Yes,
ahead.
Sir. Good morning, all of you, and good morning, sir. And today, topic of my research is on atmospheric kinetic energy spectra from global and regional NCMRWF unified models. As many of you know that we are running two global and one global and regional models from UKMO model, based on UKMO model, which is called NCUM. So I thank all the contributing others which I have given. below. And coming to the background, so as we know that accurate representation of this global kinetic energy, I'll come a little later what is a kinetic energy and other things, but the important thing is that accurate representation is very much important because it is essential for in weather and climate models, because especially it establishes a saturation bonds to the for forecast errors at each scale. I mean, what you see in the left hand figure is a scale, x-axis is a scale, and the energy corresponding to that scale. So what it represents is there is a slope spectra. I mean, there are some features which you can see from the kinetic energy spectra. So the atmosphere has some sort of canonical structure. So what it implies is that the magnitude, the spectral magnitude, which decreases with the scale, and there is a shallow sloped region. I mean, I can show you. So the 1,000 kilometers below is what I'm talking, which is decreases with scale, and there is a shallow sloped spectrum at low wave numbers and global scales, and this one k power -3, and there is a steeper power law close to -3 at intermediate wave numbers. So all these things are canonical, I mean universal. So if you do any in any model or any region in the globe, the spectra should look like this. So these characteristics are actually appeared in various many observation studies. So that's why it is called a canonical kinetic energy spectra. Okay, so I just showed some of the seminal observational studies by two important studies. One is an instrument gauge, which actually they took some nearly 7,000 commercial air flights in the upper tropospheric level, and they showed that there is a clear a deviation. Like at the synoptic scale spectra, we have a -3 slope, and at the mesoscale they have a -5/3 slope. So these are some of the important features they through observational studies they have made. So what the silent features from the spectra you can see is no system. What the others have actually asserted from their studies that there is no systematic difference in the spectrum over land and oceans, and also between summer and winter. And the K spectrum in the upper troposphere is actually should represent -3 slope at macro scales, and also -5/3 slope at mesoscale below. So these are the important spectral energy slopes they have discovered, and I mean, I'll just spend some time on what are the sources of these spectra. So basically, the k power -3, the -3 slope at the synoptic scales is commonly attributed to downscale entropy cascade. So the entropy is which is a measure of, I mean, you assume as a measure of kinetic energy of a fluid due to the turbulence. So what the energy basically comes from very low scales, like the large synoptic scales, which I have shown here, the injection here. Let me show you pointer. So this is where the injection comes. This is a -3 slope. So the last synoptic scales are the scales where the energy injection occurs, and energy is transferred from this zonal mean available potential energy through a mechanism of some sort of baroclinic process. So this is where the energy, and there is a downscale entropy cascade occurs that represent a -3 slope at the synoptic scales. Now, the other thing is -5/3 slope. There are several processes actually, because the dynamics of k power -3 spectra is still actually on debate. But there are several debate. One debate is like what we have shown, the entropy cascade from downscaling entropy cascade. Other one is upscale processes. Several studies have also shown that there is an upscale process, like what you see here. There is upscale from here and downscale from the large scales. So like this, there are two different, 3-4 different type of theories have actually proposed, but I'm not going to going into details of all those studies. So basically, the kinetic energy spectrum at mesoscale is still an ongoing debate. But it is really an important process. Actually, any model should show that -5/3 slope, because they have a strong implications on mesoscale and cloud scale, especially on cloud scale processes. So that's why it is very important. So based on this, my motivation of the study is to see our model's ability to reproduce the canonical spectrum, which is represented as evidence for the correctness of any model configuration or formulation and implementation. So this is why this motivation comes. So and also the K spectrum provides a direct measure of model filter effects, because you need to see where the energy is going. I mean, how fast the energy is going. Like for example, you see that at the mesoscale process, the energy is going very fast. I mean, that there is rapid damping of energy. So that are the type of process which actually important to see what is the effect on model coefficients, how your filter coefficients within the model are. So these are the important things. And another motivation is to see the effective resolution. I'll come to this. Effective resolution is some sort of a physical process where below which you can't, which is the process is dynamically suspect. I mean, if it not shows the -5/3 slope, which deviates from the slope, so that means that the process occurring at those scales is dynamically suspect. So there are two things. One is a nominal resolution. Nominal resolution is something like if you are taking a 500 kilometers or a 10 kilometers grid scale, your spatial resolution, your 20 kilometers is a nominal resolution, like which is called as a Nyquist frequency. So this is a nominal resolution. Effective resolution is something dynamic. So it depends on each model capability. So all these things we want to see, and so the final objective is how good our NWP models running operationally at NC model are representing these spectra at synoptic and mesoscales. And other thing is to see the extent of scales of NCM resolved, how they are resolving in our model. So which is to see the effective resolution in our global and regional models. So based on this, so I am using the data. There are various models we are running here at NCM-WF. So basically, I'm only using two models here. One is a 4 kilometer and one is a 12 kilometers global model and 4 kilometers regional model. And the period of study is June, July, August 2020. For the case study, I took this period. And the integration of the spectra is 12 hours to 36 hours. Operational forecast. So the methodology is something like this, and we are using the one-dimensional Fourier transform to each velocities in west-east directions, and the energy densities are averaged over 24-hour period at 6-hour intervals, and we usually begin our integration at 12 hours into a forecast to avoid model synapse, especially for keeping in mind of our regional model. So additionally, the energy densities are spatially averaged horizontally and vertically. So we are averaging some region and to see how the model spectra is. And we are also not taking at edges of the model boundaries because that should minimize the effects of lateral boundary conditions, especially in the case of regional model. So other thing is I am using some sort of rotational and divergent component things because to a first approximation, any flow is dominated by gravity waves, which can be distinct from other possibilities by the examination of extent to which these horizontal velocities associated with the mainly the horizontal divergence rather than the vertical velocities. As you see the mesoscales, we have some small sort of inertia gravity waves, those things with pictures. So we need to see how the rotational and divergence spectra represent our slopes, because that avoids the other complications of inertia gravity waves and small scale gravity waves, which also affect the slope of the spectrum.
2 minutes more.
Yes,
2 minutes more.
Yes, sir. I came to that. Yeah. So this is what I'm talking about. Here I showed NCM global model, and I took here a latitudinal dependence of atmospheric K spectrum. What you can see is a slope of the spectrum steepens from tropics to polar latitudes, and the tropics have relatively shallow spectrum with a quasi-uniform slope of -3 but deviates in the mesoscale ranges. But however, the mid latitude is very nicely depicted. We have two types of segments like -3 slope, and we have a -5/3 slope at a mesoscales. So this shading is a mesoscale region. Okay, so finally the polar region which have a shallow spectrum again, and the fact that this spectral slope different in different latitudinal zones is a consequence of underlying dynamics. Particularly in the tropics, we have a barotropic process which we have a small scale vortices, and while in the mid latitude we have a large scale baroclinic process where the energy is coming in a -3 slope. So that's why the dynamical process is important in the case of each different regions. Now, so basically the slope is actually well represented in the NCM global model, and also you can see the rotational and divergent components of the spectrum converge at mesoscale, which is a very good sign that our model is representing well at these scales. Now, this is a regional model boundary, and we are comparing here regional and global things at the mesoscale. So what you see here is a mesoscale slope is -5/3, and it is actually doing well. I mean, the mesoscale spectra is coming at -5/3. What you can see here, the shaded is this is a total kinetic energy spectra and rotational and divergent again. So the -5/3 is a slope is consistent with the convecting flow that lacks a broad rotational motions, which actually we saw in a baroclinic process in the mid latitude. So anyway, so other thing is effective resolution. So as I tell that the effective resolution of a model is a wavelength where our model spectrum begins to decay relative to the observed spectrum of -5/3 and -5/3 at mesoscales. So here I am showing so this is a general type of model behavior. Yes, sir.
Then control.
So, yes, sir. So what we are seeing is the effective resolution is around 20 delta x, below which we are not seeing any, the motions are really dynamically suspect in our regional models. So I think, yeah, the same thing here will come. But here we are also showing the how the model is deviating from the spectral slope at different forecast hours. So basically from 48 hours, I think our regional model is depicting well with the observed spectrum. I think here some sort of assimilation or spin-up model, spin-up issues are coming in 12 hours and 24 hours. But from second onwards, I think the regional model is very nicely representing the slope, and energy is also close to the observed spectrum. So finally, the conclusions are like this: the comparison between the kinetic energy spectrum in NW models and the expected scalings -5/3 and 3 is a way to access how well the synoptic and small scale processor resolved in the model. And the high resolution model NCMR is able to reproduce the -5/3 in mesoscales relatively better than the NCM global things. So I think I stop here. Yeah, thank you.
Any questions? I don't see. So you are saying 4-kilometer model is doing better, is it?
Yes, sir, at the mesoscale, sir.
So what is important? Mesoscale kinetic energy spectrum is important?
Mesoscale processor very well represented, even though 12 kilometers, our global model is also coming on some sort of mesoscale processes, our resolution based on 12-kilometer resolution. But still, even then, the 4 kilometers is representing well compared to the global, because it coming to close to the slope of actually universal spectra. So based on this, I think here you can actually see. So this is very close. Very close to here, you can actually see the slope is at the mesoscale. This gray region is a mesoscale portion of the spectrum. So all these processor, I mean, the slope is very well close to the -5/3 slope. But however, the problem is around 80 kilometers, I think it is deviating from this spectrum. So where we have to worry that our model is really at those scales, below that scales, like below 80 kilometers. I think we have to suspect our motions. I mean, we need to see whether any issue with the numerical stability or any model filter coefficients, the sort of things we have to see. So why it is actually deviating at the mesoscales at around 80 kilometers. What you see here is around 80 kilometers. It is really like 20 delta x. Our model is 4 kilometers, which is delta x, and 20 delta x, we need to suspect our motions from 4 kilometers to 80 kilometers.
Sir, I have one question, sir.
Yes.
Okay, go ahead.
Actually, Niranjan, you are comparing that slope at what forecast time, or it is analysis time?
Sir, this one you are asking?
That in global and regional.
So 12 hours to 36 hours. For now, I have done the analysis on 12 hour to 36 hour integration time.
Okay, so actually, main thing is that global model picks up that mesoscale little late. So if you compare between 12 and 24, it is not fair comparison actually.
Sir, I mean to say the -3 slope, I'm not worrying. I'm seeing especially on the mesoscale part.
That is what I'm telling. For global model to pick up the mesoscale energy, it takes time.
Okay. Yeah, I'll see that.
So another question is that the first 6 hours actually very important for regional. So another study actually you can continue with the spin up. What is the spin up time? That also can be seen through this study. May we continue.
Okay,
Okay,
sure.
thank you.
Thank you. Thanks for your questions.
Okay, thank you, Niranjan.
Yes, sir. Thank you.
Stop sharing. Okay. The next paper is by Rudgan Putra Pradhana.
Yes, sir.
On the theme monsoon information and prediction and for societal benefit. Can you come on screen so that we can see you for first one time at least? Yeah. Okay.
Yes, sir.
Where are you from?
Indonesia, sir.
Okay. Welcome. Go ahead. You have 10 minutes.
Yes.
Once your PPT comes online, I will start the clock.
Could you see my screen now?
Yeah, go ahead.
Okay, good morning, Dr. Raja Gopal, and also everyone. Today I would like to deliver my presentations. The title for my presentations today is Influence of Asian Australian Monsoon and Indo-Pacific SST variability on urban climate in major cities of Indonesia for low carbon building design. this is my outline for my presentations today. And as an introduction part, that building energy simulations is an essential part in developing countries. And in a scenario of climate change, we need to think a new strategies that provide greater adaptations and also resilience. And considering the local culture and not simply importing models from other climatic regions and cultures. In the specific case of hot and humid predominance, the slight variations of air temperatures and humidity during the year leads the local people to adapt and live with this condition to feel comfortable. And as we may know, the urban population growth rapidly in Indonesia is one of the low latitude Asian countries, which is all the major cities in Indonesia are dominated by hot and humid climate. And in terms of the building energy simulations, most of the hot humid climate countries need to do climate action improvements in living quality because the construction of high-rise office and apartment building has led to increased energy consumption by heating, ventilation, and air conditioning systems. And then numerous studies have been conducted as part to find the best solution for adaptation and mitigation strategies in climate change for the housing and settlement sector for hot, humid climates areas such as Indonesia and Malaysia. And in order to implement the nationwide climate change mitigation plan in the housing and also settlement sectors, it is important to investigate the impact of regional climate variability, such as Asian Australian monsoon, and also in the Pacific Sea surface temperatures over the Indo-Pacific Ocean and urban cities climate in Indonesia maritime continent. Then develop the typical meteorological year for building energy simulations is important in Indonesia. Recently, a new climate classifications in Indonesia has been proposed for passive cooling potential in building design based on the diurnal and monthly variational characteristic of weather elements. This I refer to the previous study that proposed by Dewa, and as we may know here that this is he divided the Indonesia into 8 climatic zone, consists from zone 1A to the 4B. As we can see here, the light green is the equatorial zone spreading in this equatorial area. And also for zone 1B, the sub-equatorial area also spreading in this equatorial area all over Indonesia. And zone 2A, the red color are indicate the highland tropical, which is only 3 area here. And also the zone 2B, very highland tropical, only 1 area in here, in the Papua region, monsoonal, submonsoonal, savanna, and also sub-savanna. And the objective of my research study here is to investigate the impact and response between the Indonesia major cities climate with Asian Australian monsoon indices and also SST anomalies along the Indo-Pacific region. And then to identify the temporal coherence between the Indonesia major cities climate with Asian Australian monsoon indices and also SST anomalies along the Indonesia Indo-Pacific Asian region. And some of the literature review that that I already mentioned before, that Dewa developed the climate classifications from modification of the previous Köppen climate classifications. And the study by Aldrin and Susanto has divided Indonesia into 3 rainfall zones with an equatorial pattern around the equator with 2 peaks of rain seasons in a year, monsoonal pattern, and monsoonal patterns in parts of Sumatra, Kalimantan, Sulawesi, Jawa to the island of Nusa Tenggara with 1 peak of the rainy season in a year and local patterns around the island of Maluku with the opposite pattern of the monsoonal pattern. And then atmospheric ocean interactions around Indonesia form interannual interaction of global climate variations such as ENSO and also the Indian Ocean Dipole Mode. And the dataset and methodology that I use in this research study is the three weather elements, such as average temperature, relative humidity, and also precipitations at 22 major cities in Indonesia, the daily ground observation dataset, and also the CHIRPS precipitation dataset with 0.05 degree spatial resolutions, and this is data available from 1981 to 2021. And the three monsoon indices, like Indian Summer Monsoon Index, Western North Pacific Monsoon Index, and also Australian Monsoon Index. And as we can see here, also I use the Indian Ocean Dipole Mode Index, the monthly basis dataset from 1870 to 2020, and also multivariate El Nino Southern Oscillations Index. This is the bi-monthly indexes from 1979 to 2020. And the lag correlations analysis method was applied to examine the lead-lag relationship to identify the temporal coherence between the major city, climate with Asian Australian monsoon indices, and also SST anomalies along the Indo-Pacific Ocean region. And then this figure shows the Asian Australian monsoon and Indo-Pacific SST indexes. As we can see here, the red box in the left side are indicating the Indian Summer Monsoon Index, which is defined from the zonal wind in 850 hectopascal, the differential of zonal wind area average from this zone 1 with zone 2. And this the right side, the Western North Pacific monsoon indices are defined by the difference of the area average from the zonal wind at 880 hectopascal from this domain 1 with the domain 2. And this is the Australian monsoon indices, and also the Indian Ocean dipole mode here are defining from the differential between Eastern and Western. And also the last one that I use the multivariate El Nino Southern Oscillation Index, that this area was calculated from the 6 main observed variables over tropical Pacific, such as sea level, pressure, zonal and meridional component of the surface wind, sea surface temperatures, surface air temperature, and also total cloudiness fraction in the sky. And
2 minutes more.
Okay, this is the location of 22 representative major cities in Indonesia. And also the daily weather data distributions from Jambi to Sumeneb, from zone 1A to 4B. And this is the monthly average of climate variables at Palembang for the illustrations that I take one city as an example. This is the average precipitation, relative humidity, and also temperature. And as a cross correlation function, I analyze the optimum value for each parameter like precipitation, relative humidity, and temperature. And as we can see in here, for example, this at Palembang, this during the dry seasons are strongly affected by the Australian monsoon index, and during the wet seasons are strongly affected by this ISMI and also Western North Pacific monsoon index. And then I trying to compare this is by using the observation stations for precipitations, as we may can see in here by the BMKG dataset, the correlation between the precipitations and also the regional climate indices, most of the part are having very low correlations, and also some part are having small to moderate correlation. And this is the distributions.
Please conclude.
Yes. Yes, sir. Okay. And then As a summary and discussions, this Zone 1A and 1B shows unclear relationship with all regional climate indexes for precipitations by using ground observation dataset, but a bit improved after use the CHIRPS dataset. Then clear relationship with monsoon and SST for relative humidity and also average temperature. And then for Zone 2 and 2B, mostly affected by the Australian monsoon and ENSO during dry season, and Indian summer monsoon, also Western North Pacific monsoon, and dipole mode during mid season for average temperature and also humidity. Meanwhile, for precipitations affected by the monsoon clearly shows only in Chiteco during dry and wet seasons. Okay, that's all. Thank you very much, sir.
Thank you. Are there any questions? Okay, there are no questions. Thank you very much. Can you close the screen?
Oh, yes, sir.
The next speaker is Dr. Raghavendra Ashrit on high impact weather, monsoon weather.
Am I audible now?
Can we see you? Okay.
Yeah, my camera is on. I understand I'm audible.
Yeah, go ahead.
Yeah, thank you, Chairman. So this is the topic which I listed, seeps and sedimetrics for verification of model predicted extreme rain over India. I tried to do some analysis for the recent years. I wish to acknowledge a lot of earlier works of Mark Rodwell, Rachel North, and Chris Farrow from ECMWF Metofis and Exeter University. I wish to acknowledge them. I have taken that background work and inspiration from there. I'm moving to my next slide. So some of the challenges that we have in verification, especially for verifying the extreme rains and heavy rains, it's like we have challenges from observations. We often don't get very high resolution quality controlled observations to verify these events. And some of these events are very rare and like they're poorly observed, they occur in unpopulated regions. So there is a lot of uncertainty when it comes to sample size and things like that. So if we tend to pull data from all surrounding regions, then issues of homogeneity all crop in. So important another challenge is from the statistics side, statistical properties side, in the sense like extreme values are characterized by very large values, and often quality controls reject them as outliers, and so it becomes very difficult to handle. And also statistical measures have the difficulty that like there are no robust measures for treating the values near the tails. So standard verification scores that we use, they always tend to give very small values, trivial values, which don't make sense, and often forecaster and verification methods like tend to ignore these small.
Asrit, your voice again gone actually. Dr. Asrit?
You're not audible. Not audible,
Yeah,
not audible.
Now?
Yeah.
Now it is audible?
Now it's fine.
Yeah, when I was moving the slide, I think it got muted. So seeps and sedimetrics are two metrics that are specifically designed, and they could be used for this particular purpose. And they are actually complementary measures of performance, and they use climatological distribution of precipitation at each location to define the thresholds. They assess locally important aspects of the forecast, so that like once they are expressed relative to climatology, they can be aggregated across climatologies and different regions. That's one of the important. And additionally, they are resistant to hedging, so that there is no undue high skill due to excessive number of forecasts and things like that. I'll move to the next slide. Yeah, first I'll just touch upon the stable equitable error in probability space, SEEPS. It's a measure in probability space rather than the measurement space. As you can see on the right top corner, I have a graphic which SEEPS allows you to segregate your entire rainfall ranges into 3 categories. One as dry, you can put some threshold. The standard like ECMWF who designed this metric, they took 0.2 millimeters to define dry, and the remaining portion of entire precipitation is divided into 2 categories based on the probability of occurrence. It's divided into light and heavy rains. So the probabilities are distributed in such a way that your probability of heavy rain is half the probability of light rain. So you have 3 categories like dry, light, and heavy. So your light rain has double the probability of heavy rains. So this type of classification allows you to like for any region, you can like dry region, wet region, wherever you go, like you can have these type of classifications, and accordingly do the verification for 3 categories. So
Dr. Asrit, again, you are not
Mute.
you are not audible.
I don't know, whenever I move the slide, it is getting muted. I'll just try to go back now. I don't know, like
Sir, I think you can off your video and try.
yeah, maybe I'll try to do that. I've stopped my video now.
Yeah, please continue.
But the difficulty is like moving off my slides. Maybe I'll change the layout, possibly that will help. I don't know. Am I still audible?
Yeah.
So yeah, this is the metric, and it is defined as a scalar product of the 3 elements of the contingency table. It allows you to specify the entire skill in terms of it's an error metric, and you can express it as 1 minus SEEPS. So that for error metric SEEPS, it is like 0 is the best forecast and 1 is the poor forecast. You can you can orient it positively by expressing it in 1 minus SEEPS, and this is one example of verification carried out for different models for the globe as a whole. And you have like a day 1 forecast measuring like giving a very good high metric, and the skill is decreasing in time with higher lead times. I'm moving to the next slide and just allow you to see for individual cases how this should look. The graphic shown here is for a case of heavy rainfall on 5th September 2019. The top left panel shows the observed rainfall from the gridded gauge versus satellite merged precipitation. The middle panel on the top shows the NCUM forecast valid for the same day. We can clearly see that there are some regions where the model is able to predict heavy rains, especially in the bottom, and not necessarily matching with where observation actually happened. There are some regions like where the model is predicting excessively high compared to the observations. So just for the moment, we just shift our focus to the bottom panels, bottom, middle and left panels. The forecast is expressed. I'll just go back. Forecast is expressed in terms of observed, and the forecast are expressed in terms of the dry, light, and heavy rain categories. The top 2 panels are expressed as dry, light, and heavy precipitation. And here we can clearly see the glaring differences in the bottom middle and bottom left. Okay, so SEEPS allows you to actually give an integrated measure of the performance based on all the regions where the forecast was in correct category, and penalize the forecast where it was not in correct category, and things like that. So on any given day, so if we shift our focus to the bottom right, here is your 1 minus seeps indicated here. So definitely wherever the model was predicting in the wrong category, you have very, very low 1 minus seeps value. It's less than 0.1 and 0.1 and 0.2 and the blues and purples that you see. And wherever the forecast was in correct category, you have relatively higher quantity. I'll move to the next slide now. I hope I'm still audible. Yeah. So this is another example of the heavy rain over Kerala. This is from the 9th of August. The date stamp is missing. I'm sorry for that. This here clearly we can see the just if we can focus on the bottom 3 panels, we can clearly see the observed rainfall is showing heavy is predicted everywhere, and the forecast is also showing heavy predicted. And accordingly, you have a very high metric which is exceeding 0.8, and that is correctly shown. And wherever on the eastern periphery of the domain where the model is still predicting a relatively lighter rain compared to observations, you have lower metric. So completely like yeah, I'm almost done. So focused like completely based on several such episodes for 2016 to 2021. We have put up a score here just that shows how we have improved skill when we do verification at all India scale, and as we move to the smaller regions, we have relatively poor performance. So we just move on to the next SEDI metric that I wanted to discuss about. This is again focus is on the extreme and rare events. It allows the user I'll quickly move ahead and skip some of the background information just to show that it allows you to express all the elements of contingency table in terms of hit rate and false alarm, and make the verification score base rate independent. That is the philosophy of using this SEDI metric, and it has several useful properties. This is the formulation. It allows you to express the verification metric from -1 to +1. 1 stands for the perfect forecast. And similarly, like traditional metrics, they tend to allow very, very low values for higher rainfall thresholds. And we can see SEDI metric allows you to express it and bring meaningful values at higher rainfall thresholds. This is also for 2016 to 2021. So this is now like pretty much there are several properties which are desirable properties of this verification metric that are discussed in Ferro's paper. Now these are very standard verification metrics, and we can clearly see from ECMWF publications also it is routinely used for assessing the forecast of 90th percentile, 98th percentile, and how our model is performing over the years with improved resolution, whether we are able to correctly predict the extremes or not. Similarly, the right side also we are able to show from NCMRWF in the last few years how forecast of rainfall exceeding the 90th percentile, 80th percentile, and things like that. So extreme rains we are able to express the improved scale. So just I wish to conclude it with the summary of the discussions that we had here. That's all. Thanks.
Okay, thank you. Any questions?
Sir, this is Bushair from IMD. Sir, what we are last 2021 monsoon, what we have seen is that in some of the cases, NCM rainfall is over predicting. So have you looked into this case?
Yeah, like you will always have such cases of over prediction, some cases of under prediction. Generally, what happens is this rainfall is slightly displaced. Even if it is displaced by about half a degree or less than that, you always end up like over the regions where it is not raining, you will always have over prediction. Such cases will always be there. So best is always to use metrics like this, which will penalize where it is over predicted and give you an integrated measure of overall performance.
Yeah, my questions are related to same line. Means just now Dr. Asrif told that the displacement, it is actually main concern in the forecast. So sometime model predict the rainfall but at wrong place. So how much it can accommodate these scores actually? Means suppose half a degree or if it is 1 degree.
See, when we are doing verification for all over India, like it will give a complete integrated measure. So whatever displacement has happened within that, accordingly it is penalized. Okay, even if it is half degree displacement or a 1 degree displacement, the integrated measure will thoroughly penalize if this thing is there. But specific event wise, if you have to do, then you will have to go for CRA or more type of verification measures which are focused on a smaller region, and event wise you will have to have that type of assessment.
Okay,
Okay, thank you. Yeah, the next paper is by Praveen Kumar, bias corrected extended range forecast of rainfall in operational framework of IMD. Can I see who is speaking?
Yeah, I'm audible.
Yeah, go ahead. 10 minutes.
Good morning, all. Good morning, sir. Myself, Praveen Kumar from India Meteorology Department. I'm going to present my research outcomes, and that is titled as Bias Corrected Extended Range Forecast of Rainfall in Operational Framework of India. So I would like to brief about how IMD running the different models for the different time scales and for the different grid type operational forecast. So these are the short range, medium range, extended range, and long range. For short range, that is right for the 3 days. WRF model, that is the regional model, is being run at the IMD at the resolution of 9 kilometers and 3 kilometers for the period of 3 days, and this is run for the twice daily. And for making the medium range forecast, that is right for 3 to 10 days, two models are run at resolutions of 12 kilometers. First is the GFS, that is the Global Forecast System Atmospheric Model, and this is run for 4 times daily at the UTC of 0, 6, 12, and 18. And this is also run for the 10 days, 4 times daily. Similarly, for medium range, another model GEFS, that is the ensemble of 20 members and run for the 10 days, once a day, and at the result of 12 kilometers. For the extended range forecasting, IMD runs models, climate forecast system version 2, couple model, that is the ensemble of 16 members, and this runs at the resolution of 38 kilometers for the 32 days. And simultaneously, there is handcast run for also made for 18-19 years based on the runtime. So this is made for the weekly run and based on the Wednesday initial conditions. And the outcomes of the 38 kilometers are further processed at the resolutions of 50 kilometer grid resolutions. And for making the long range forecast, that is months to a whole season forecast, climate forecast system model, the symbol of 20 members are used run. That is valid for the for 4 to 6, 7 months, and that runs once in a month. And the resolutions in it are 38 kilometers. So I will be focusing here for the performance of ERF in simulating the Indian summer monsoon rainfall for southwest monsoon of 2020 in extended period over the selected river basins of India. So I just want to give the little bit glimpse of the ERF. So IMD, as discussed, IMD runs extended and forecast of use ERF system for making the operational forecast of rainfall and temperature and different weight parameters also, and that is based on the coupled model climate forecast system version 2. So there is a complexity in the coupled and atmospheric ocean land ice interaction nature of the monsoon. It is very challenging to simulate and predict very accurately the intents of monsoon at various spatio-temporal scales. And this complexity arises due to the gap between medium range and seasonal weather forecasting. And this remains the most challenging task since the time scale of this ERF is sufficiently long, that is up to the 1 month, so that much of the memory of the atmospheric initial condition is lost. So that also makes very complex and a little bit difficult to make the accurate predictions. However, there is much improvement have been seen in these models due to the continuous improvement in the models, better initial conditions through improved satellites and other observations, and expanding high computing capability. These have shown that there is improved in the skills in simulations of these parameters with parameters like the rainfalls and temperature at various spatial and temporal scales. So actually, I evaluated the ERF for the Southwest Monsoon of 2020. So I just would like to give a glimpse of salient features of Southwest Monsoon 2020. So actually, this was a very unique monsoon year, as it received approximately 109% of long period average, and that time there was on-time arrival of over the Kerala coast, and there was also observed of the intra-seasonal variability of the rainfall. And during the month of June, during the Southwest Monsoon, there was a deficiency of rainfall, and that was due to the east-west trough at mean sea level extending up to the lower tropospheric level with cyclonic circulation, and that caused a reasonably widespread rainfall over the entire country. And when we see at the different regions, so South Peninsula India received approximately 130% of LPA, followed by the Central India that received 115% of LPA, that is long period average. Northeast India received the 160% of LPA, and Northeast India received the deficit of rainfall during the Southwest Monsoon 2020. That remained only 84% of total LPA. So this diverse characteristics of the Indian monsoon in intra-seasonal over different parts of India offered a scope to various sectorial application, and especially to the hydrological sectors, because there is an urgent need of discharge and making the stock of water at the weekly basis or even the monthly basis. So this is the suite of ERF models. So these are the couple models of ocean and atmospheric coupling is there. So for the ocean, there is a model of CFTL, modular ocean version 4 is used, and for the operational suite of models consist of the CFS-V2 T382 and T126, and another two is a GFS bias corrected, that is the SST at T382, that is the 38 kilometer, and GFS bias corrected at T126 with 4-inch symbol each. So there is a total of 16-inch symbol in for ERF system. So this is my study area. Actually, there are a total of more than 150 river bases, but I have opted only 9 river bases on experimental basis to see the performance of rainfall during the Southwest Monsoon. So I have also taken the weekly wise accumulated rainfall for each river basis, and that weekly rainfall is very crucial for the dam in preparedness for their stocks or release of the water at the correct time in advance. So we can see here the scale of ERF over the different meteorological subdivisions during the Southwest Monsoon 2022. So we can see there is a variability in the scales over the week period. Means week 1 to week 4. When we move from week 1 to week 4, the scales are getting poorer over the space. However, for the some regions, the scales remains very significant, and a high CC are shown. So during the week 1 period, a high significant CC, that is more than 0.7, was observed for the west coast. For the west coast, west and east Rajasthan, Saurashtra and Kutch, and Gujarat regions, East Madhya Pradesh, west coast regions. This is the west coast regions, Marathwada, Assam, Meghalaya, and Sikkim Met subdivision have shown very good CC during the week 1 period. So when we move on the week 2 period, there is a slightly decrease in the CC over the regions, and however, a high CC of the range of again 0.7 was observed for the regions of Jammu and Kashmir, Ladakh, Himachal Pradesh, West Uttar Pradesh, Gujarat regions, Chhattisgarh, and coastal Karnataka. And similarly, we can see that over the southern tips and the eastern part of the country had comparatively less week 2 onwards. So we can see here that the skills are different over the space, means different weights of divisions shows the different skills in the predicting the ISMR rainfall, and for the week period also. So this was the time series for the IMD observed rainfall on the weekly basis for the different initial conditions for the total of 18 weeks during the monsoon season from 1st June to 30th September. So we can see that these bars show the different weeks of the different colors. So there is some intra-seasonal variability as we can see, and sometimes overestimations and sometimes underestimations of the rainfall by the models here. So there is systematic bias around the all across the week period, and this gives the scope of further bias corrections. So this is the result that shows how the CC and RMEC and mean absolute error vary from. So still the ERA forecast shows result for the week 1 and week 2 for most of the river basins. We can see here week 1 and week 2 shows the most good skills, means high CC and lower RMSE during the week over most of the river basins. And one of the probable cause of these biases indicate that model lacks proper representations of the subgrid scale process in some or all of the convective microphysicals and boundary layer parameterization schemes. And the uncertainty associated with the parameterizations of the subgrid scale process gets affected the model's inadequacy in simulating synoptic conditions. As a result, there will be location error. That is a spatial shifting of the forecast rainfall as well as the intensity error. So we can say that may be the assumption that the spatial dimension of the river basin is smaller. Hence, the error in the model rainfall forecast over the basin scale may arise either due to the location error or also adding due to the intensity error. So this is the probable cause of why the different basins show different biases in predicting the rainfall in the year over the week periods. So further, I applied some bias correction method to see the results, how there is improvement in the accumulated rainfall on the weekly basis. So I opted for the normal ratio correction method that has been suggested by the WMO recommend. So this is the formulation that I applied on the weekly basis. So this is the ratio, that means this takes the observed climate flow G for the week, particular weeks with the model climate flow G. Observed means IMD observed, and model means that the hindcast runs, I took the climate flow G from that, and that ratio get multiplied with the raw forecast of the model, and that gets the bias corrected forecast. So this is the method I opted to make the bias corrections. So we can see here the basins having the lesser spatial extents have much improvement in correlation coefficient, as well as there is reductions in the RMSE error also. So the main finding was that those basins having the larger spatial extents having the good skills in the raw forecast, but those basins having the lesser spatial extent having the less skill in predicting the monsoon rainfall for this period. So after applying the bias corrections with a normal ratio, we can see that there is improvement in the error in terms of RMSE, and CCs are also improved here.
More.
So I would, yes, sir, that's it. So we can conclude that in most of the heavy rainfall events during the monsoon season 2020, the intra-single gravity captured very well, except over basins having a small spatial extent. However, when we analyze over the meteorological subdivisions of India, the spatial correlation was found to be reasonable and significant up to week 3 period. And further, while applying the normal ratio corrections and advancement in this skill is observed in terms of CC and RMSE, this error has been observed. So the model performance indicate here that ERF may be utilized for various hydrological application in lead time of 2 to 3 weeks at least. And the same may be extrapolated to other bases. I have exercised here for only 9 bases, as total of more than 150 bases. So same method may be applied and exercised for the remaining bases having the different spatial extent. Thank you.
Chat box questions.
Yes.
I have a question.
Who is it?
Raghu.
Yes.
Yeah, go ahead.
Mr. Praveen Kumar, can you just go to that table which you showed before the summary? There, like over Narmada, it appears to be deteriorating. Can you see, you consider it a large basin or a small basin?
My screen visible?
Yeah, here.
This one?
Next one. Yeah, this one here.
Yes.
Over Narmada, you can see 0.68 to 0.4. 0.0808 is as it is.
Yeah,
So
I can
Narmada,
see.
actually, it's not, it's spoiling.
Yeah, actually, there is no consistency. We can also see that
Yeah.
I just found that the basins having lesser exponential strengths like the Iduki, Idamalar, those have shown much better skills. But when I applied the same techniques to the basins having the larger exponential, that have shown not much improvement. So this is most applicable for the basins having the lesser expression that have shown very not much good skills in the raw forecast. But after applying this bias selection formulation method, the smaller specification basins have shown good results.
So just one clarification, like this bias correction is happening at grid scale, actual model data you're doing, and bias correction is applied at grid to grid.
Yeah, that might happen, and the less number of grid is also incorporated when we take the lesser special extent of this basins. So this gives the accumulations error also, location error.
I think there are no more questions. Thank you, Praveen.
Thank you, sir.
I'd like to thank all speakers who kept time and we could finish in time. And I'd like to thank the organizers for giving me a session. Thank you. Anand, take
So
it.
reached to the end of this session. Thank you, sir, Dr. Rajagopalji, you for nicely coordinating the whole session. And thank you to all speakers to cooperate with time. And so we'll be again joining in the next poster session. There is in between. So main session will be in the evening, but there is poster session just after this. So hall within it will be available in hall A. So please join there. So again, thanking our session coordinator, Dr. Rajagopal. So we are ending this session, sir.
Thank you.
Yes, sir. Yeah.